So last but certainly not least, we have Brian Lorenz, who is joining us from Pomona, where he is going to be a rising junior this year. Brian's been working over the summer with Dan Kelson, studying the spectroscopic redshifts of a very large number, as you can see, of low-mass galaxies in the cosmos field.
All right, thank you, Gwen. So we're interested in how galaxies evolve over time, especially in regard to star formation. Do they form all their stars very early, very rapidly? How do they form their stars? And so there are a couple ways to explain this. So Dan Kelson here has been working on a stochastic processes approach to star formation. And that is derived solely from first principles, only assuming that star formation is a non-negative stochastic process. And it predicts a number of observables, including the scatter and star formation rate for low-mass galaxies. It might not work for higher-mass galaxies, as those could become so large that they disrupt the environment around them, deviating from a purely stochastic process. There have also been simulations using FIRE in 2016, and they predict that star formation rate should correlate with galaxy size. So if you have a lower-mass galaxy, you should have lower star formation rate. Also, looking at this plot, we have specific star formation rate on the y-axis, and so that's star formation rate divided by mass. So this is a measure of star formation that is independent of galaxy size versus time. And over here, we have a Milky Way-sized galaxy, and we see that star formation is fairly constant in recent times, whereas the lower mass galaxies have more bursty star formation. So if we get a population of low-mass galaxies, we can test for all these observables. However, getting that population is not so easy, because the local universe is not representative of the universe at large. We need to look to a higher redshift to get an unbiased sample of low-mass galaxies, and that puts some constraints on our redshift. Also, low-mass galaxies are just intrinsically faint because they are of lower mass. So that sort of sets a lower limit on how massive the galaxies that we want to look at are. And so the Ultravista catalog, which I'll talk about more in just a minute, probes very deep. And so here is the mass of the galaxy in log stellar masses versus redshift. So in our mass and redshift range, the Ultravista catalog has all of the points in orange, and we've taken a random sample in these blue points. And so the Ultravista catalog works on the cosmos field, which has been observed by many major telescopes, including the Hubble Space Telescope. And so the Ultravista catalog used the Hubble data and classified which objects were galaxies and fit them to find photometric redshifts. So you look at the overall energy distribution of the galaxies and compare them to known templates, and that gets you the redshift. So that's how we were able to select our sample of galaxies. And so Dan did the observing at Magellan with 8 observations in February 2016 and 2 more in 2017, revisiting some of the objects with low signal to noise, as well as some new objects. And everything was done on the IMAX spectrograph. So I received about 1,400 data files that looked like this. So I need to figure out how to get from this to an actual spectrum. And so we can see in the center here is sort of the object signal. And we need to automate this process, right? I can't do this for every object by hand. And the width of this might change based on the object, or sometimes there are 2 objects in the slit, or something like that. So to do this, you can collapse this entire thing along this axis, and then so turn it sideways. So the y-axis here has now become the x-axis. And you'll see the signal of the object forms a Gaussian profile. And so we can fit that signal with a Gaussian, obtain a mean and standard deviation, and by extracting over the region 1.4 standard deviations on either side of the mean, you get the spectrum with the highest signal to noise. So from that, we go to a spectrum like this. However, it's still contaminated by the atmosphere. So the atmosphere is a strong absorber in the infrared, and these features that I've circled here are not part of the galaxy spectrum. They are just the atmosphere's imprint on that light that's coming to us. So to correct for that, we take a hot star in each mask, and the hot stars are going to have very few spectral features because their atmospheres are fully ionized. And so the features that we see will be the atmospheric absorption features. And so you can fit that star with a polynomial and then divide that out, leaving just the atmospheric features to generate a correction file like this. And so we take our galaxy spectrum and divide it by this correction file, and you get a spectrum like this, where the circled features are now absent in the lower spectrum. So I've run this through all 1,400 objects, and we get spectra like these, and now we have to measure redshifts. So to do that, we're going to use a technique called cross-correlation. And so first we continuum subtract the object and the template. So you take a known template and your object, you remove the shape of your detector so that everything's at a baseline of 0, and absorption features will drop below this, and emission features will be above this. So if we take the template here, you multiply everything pixel by pixel. So like the -2 here, we'll multiply with a 0 up there to give you 0. You add up all the pixels, you still have 0 here. But if we take the blue template and shift it slightly, then you'll see it starts to correlate a little bit. The -2 and the -1 multiply, and when you add it all up, you get 2. And if they match up perfectly, you'll have the highest correlation. So we do this technique using spectral templates for the galaxies. So we use 5 templates from Sloan Digital Sky Survey, ranging from a red dead galaxy to a blue star-forming galaxy, and the other templates fall in between these. And we're going to correlate these with our galaxy spectra. However, we don't want to just automate that process. This is something that you want to check every single one by eye, in case it correlates with a cosmic ray, or there's some sort of contamination that isn't obvious. So to do this, I've been designing a tool that allows you to easily go through all of these objects. So in the top right, we have the original spectra, the original FITS file, with the green region showing what was extracted in my earlier step. And that gives you this spectrum, which is now corrected, and the blue, which is overlaid, or the orange is overlaid in the blue in most of it. The blue is the spectrum, and the orange shows the regions of the spectrum that we're going to consider for the fit. So one of the great advantages of cross-correlation is that you can exclude bad data. So you'll see sort of in this region here, you've got some bad sky subtraction, and so we exclude that data in the fit. And that also allows you to keep all the emission lines or cut those out, those sorts of things. And so you can fit over just this black region. We've chosen that because sort of towards the ends, the detector is more noisy. And so we can tailor the math specifically to each object. So then here is the correlation coefficient, the plot of correlation. So we've taken one template, this is template 27, put it at a redshift of 0.2, multiplied it pixel by pixel over the region that we're considering, and then that gives you the value on the y-axis. And then you shift it slightly and do that again at all of these redshifts. So up here, we see all of the templates, all of their redshifts. And this also takes the template and overlays it on the continuum subtracted galaxy spectrum. So in black is the template shifted to the current redshift. So the redshift that you're looking at now is indicated by the green line, and you can move that around. And so this is a case of very clear emission. If we look down here, this is a zoomed in region of this top plot. And we see that the template spectrum overlays nicely with the galaxy spectrum. So all 3 of the emission lines line up nicely. And most of the templates agree, except for the red template, which doesn't have any emission. So then there are some clear cases of absorption. If you look at the H and K lines here, they line up perfectly. All the templates agree. So that one's pretty clear. But then you get some cases like these, where maybe it's this peak, maybe it's that peak, we don't quite know. And so for these, I have a button down here that I can just check off and mark them as unsure. And these are the redshifts that I'm not confident in. So to go back and to try to recover some of those, I improved the interface a little bit, putting lines where the emission and absorption should be over here, but most importantly, adding this. So this plot takes known spectral lines, emission and absorption, or emission in blue, absorption in red, shifts it to your current redshift, and overlays it with the original galaxy spectrum. So this one, where even though all the templates agree, this isn't a particularly high peak, I'm not super convinced by this. But when I look at this plot, these 3 lines right here, the middle one of them is H alpha. And this galaxy has a huge spike at H alpha. So this allows me to be confident in the galaxies that maybe I wasn't so confident before. And so when I did the first pass without the updated interface, I got around 80% of the galaxies confident. And then after updating, we recovered another 100 galaxies. You'll see that most of the galaxies fall in our intended redshift range between 0.3 and 0.4, with some galaxies falling out, and that's just due to photometric redshifts not being perfect. They're not as accurate as the spectroscopic redshifts that we've been attempting to measure. And so some other checks that we can do to make sure our results are consistent. This is from the paper that compiled the UltraVista catalog. Between 9 and 10 solar masses, we see that roughly 20% of galaxies should be quiescent. And if you look at our breakdown of correlation by template, the ones that correlate with template 23, the red template, form 21% of our total galaxies. So it's nice to see that that's consistent. Also, the galaxies tended to correlate either with 23 or 27, and very few with the ones in between, which is consistent with galaxies switching from star forming to red and dead very quickly. So to add some more confidence to our measurements, we can look at the 194 objects that were observed multiple times, once in 2016 and once in 2017. And so each redshift measurement was done independently. I didn't consult like the first redshift measurement when measuring the second one. And for these blue points here, these are ones that I didn't mark as unsure on either of them. So I was confident in both of these measurements. And we see that every single time they line up, they gave me the same redshift. So that doesn't necessarily mean they're accurate, right? I could be wrong both times, but it does mean that there's some sort of consistency here. And then these yellow points are ones that I was able to measure once, but was unsure in the other measurement, and the red points, I was just unsure in both. So we can also try to characterize our uncertainty in these measurements. And if we look at the velocity differences for galaxies that were observed multiple times, we see that they spread on the order of maybe 50 kilometers per second, which is low enough to give us some idea of galactic structure. So we can figure out which galaxies are nearby other galaxies and get an overall shape of the galaxies in our field. Finally, we still have 150 galaxies that are unsure, and 152 spectra that I marked as unsure, so spectra that could possibly be recovered if they're looked at more closely. And we notice that though we tried to avoid bias as much as we could in our sample selection, we are biased in our measurements. So this is, again, specific star formation rate, so star formation rate that's independent of mass versus the stellar mass of the galaxy. And we see that systematically the galaxies that we are still unsure about are low mass and low star formation. And that makes sense, because lower mass galaxies are going to be dimmer, so we're going to have lower signal to noise, as well as lower star formation. There's a lower mass to light ratio, because you don't have the young stars that are emitting as much ultraviolet radiation. And so those are going to be harder to obtain as well. So our sample here is still biased. However, there's a fairly effective technique for recovering some of these, and that is giving the spectra to Dan. And so he has gone through 2 of our 10 observations and looked at them more carefully using his tools and was able to recover 14 galaxies. So at this rate, after going through the other 8 observations, we're expecting to recover about 60 more. And the ones that he recovered are in this region of low star formation and low mass. So while we can't remove this bias at this rate, we might be able to alleviate some of it and be able to better describe the sample as a whole. So in future work, we hope to continue to figure out the redshifts of the remaining galaxies here, then measure their star formation rates, and test the plausibility of the stochastic processes approach and the simulations. Thank you.
All right, question, Brian.
So those unsure bad points at high mass and high specific star formation rate,
Mm-hmm.
do you know why those, why you guys were able to measure redshift for those guys?
Yeah, so there could be a couple of reasons. I think the most likely, I have some plots through with other metrics, but I think the most likely is just poor extraction. So maybe I missed the actual region where the spectrum is in. Yeah, I think that's probably the most likely reason for those. But yeah, we could revisit each point individually and take a look at those.
Other questions? Do you know how you're going to measure the star formation rates?
We can look at the strength of the hydrogen alpha emission is my understanding, but I still need to do more to understand exactly how we get star formation rates out of these. Yeah.
Any other questions?
Hmm?
Could the GUI that you created be easily applied to other data or instruments?
It depends sort of, yeah, which step of the GUI. I think the cross-correlation one, certainly if you are trying to like correlate two things, I guess, then yeah, it seems like that could be modified fairly easily.
The low mass, low star formation rate objects are obviously low signal noise.
Mm-hmm.
Does your, in your cross correlation method, do you degrade your templates to their signal to noise? Is that an integral part of it?
Yes. So the same process that we use to, so I guess the Galaxy is first continuum subtracted and then weighted by the like inverse of the variance. So we apply that same process to the template. We weight the template by the inverse of the variance of the Galaxy spectrum as well. Yeah.
All right, let's thank Brian. All right, so that concludes our symposium.
This would be a great time for me to interrupt and thank Gwen.
I would like to have one more round of applause for our 10 remarkable students who joined us this summer. So, welcome. And with that, there is cake and ice cream and sorbet outside, so we can all celebrate. So.